decides when we start.
Yeah, we start now. Yeah. Okay. So,
Okay.
yeah, good afternoon and good evening, everyone. So today,
recording in progress.
Professor Frederick Wagman will go on to give us the mini course. Let's welcome.
Yes, thank you. Thank you very much. So this is my second lecture in this mini course, and I will be talking about the cohomology of racks. And this owes very much to my former thesis student, Simon Proves. Yeah, and so I am. Most of what I will be talking about is what I understood in connection to his thesis or what he explained to me. Okay, so actually, I will start with a small historical sketch. Yeah, the motivation. The motivation for many of these exotic structures, which I talk about here in this mini course, are due to Jean-Louis Laudet. And his search for explaining the non-periodicity of algebraic K-theory. Yeah. Non-periodicity of algebraic K-theory. So let me sketch what this is all about. In topological K-theory is the study of vector bundles on a manifold. Yeah, and these vector bundles have structure groups. Yeah, and so a vector bundle has as its structure group GLNR, and so there's a relation between the vector bundles and principal GLNR bundles. Yeah, and so on orientable manifolds, you can then go down from GLNR to the orthogonal group. Yeah, ONR, and so. In this way, the topological K-theory on a manifold is related to homotopy groups of some groups. Yeah, and so what Raoul Bott showed is that these homotopy groups are periodic. Yeah, for the orthogonal group. Yeah, I'm not taking just the orthogonal group ON of R, but I'm stabilizing. Yeah, I'm including the matrices of the orthogonal matrices of size n into orthogonal matrices of size n+1 and then n+2 and so on, and I'm taking the inductive limit. Yeah, this is the big orthogonal group, which is denoted O infinity, and Raoul Bott showed that the homotopy groups of O infinity are periodic of period 8. Yeah, and this explains some periodicity phenomena in topological K-theory. Yeah? And exactly the same for the complex K-theory. Yeah, there it is the unitary group which plays the role of the orthogonal group in the real case. And there it is 2 periodic, yeah, periodic with period 2, yeah. And so Jean-Louis Laudet thought about algebraic K-theory and So what is algebraic K-theory? Algebraic K-theory is an invariant of a unital ring A, and what the modern way of defining K-theory is that it is PGL infinity of A plus. Yeah. So what you're doing is you're taking matrices with values in this unital ring A, and you're doing the this inductive limit construction, yeah, in inserting matrices of size n into matrices of size n plus 1 and so on, the inductive limit. And then there's a plus construction. I will not talk about this. And then the Kn of A is the homotopy group of this topological space. This B is the classifying space of this group. Yeah, but this is not very important. Yeah, this is just to tell you how this is defined. And so it turns out that topological K-theory can be seen as this algebraic K-theory, but for the ring of continuous functions or infinity functions on the manifold. Yeah, in this special case, you get back topological K-theory. And so the question of Jean-Louis Laudet was, topological K-theory is periodic. Why isn't algebraic K-theory periodic? And so it is known that this algebraic K-theory has been computed for many rings, and so it's known that it is not periodic in many special cases. But Jean-Louis Laudet's question was, how do you quantify this non-periodicity of algebraic K-theory? Yeah, this is the question. And so in order to quantify it, Laudet came up with the following reasoning. In fact, this very complicated definition is much easier over the rationals. Yeah, over the rationals Q, you can express K-theory simply in quotation marks, simply in terms of group homology. Yeah? It turns out that the homology of this GL infinity of A, trivial coefficient in Q, is in fact a Hopf algebra, a graded Hopf algebra. And as such, it is the exterior product on some primitives, and the primitives are the K groups. Yeah. K theory as primitives, primitive element of the Hopf algebra, of the graded Hopf algebra. Which is the homology, group homology of the K. Yeah, and so this is a very nice link between group homology and K theory. And so it also works for the associated Lie algebras. Yeah, and this is what is called the Laudet-Quillen-Spigan theorem. And you do the same thing, but with the Lie algebra homology of the Lie algebra of infinite matrices over A, which values given, then this is also a Hopf algebra, and the primitives are now what is known as the cyclic homology of A. Yeah. Cyclic homology as the primitive elements in the braided Hopf algebra A, which is the Chevalier-Eilenberg homology of GL infinity of A. Trivial values. Yeah. Okay, and so when going from this group here to its Lie algebra, in some sense, this is the Lie algebra of the group GL infinity. Yeah, then you go from, in some intuitive sense, go from the lower level to the infinitesimal level. Yeah, and so this is why cyclic homology is also called infinitesimal K theory. Yeah, and so it turns out that you can measure the failure of periodicity of the infinitesimal K theory. Yeah. Can measure the failure of periodicity of the infinitesimal K theory. In fact, it is given by the so-called exact sequence, exact sequence. Named after Alain Connes. Okay, this sequence starts with HHN. This is Hochschild homology of A, goes to cyclic homology of A, goes to cyclic homology 2 steps down, and goes to Hochschild homology 1 step down, and so on. Yeah, and so this exact sequence measures the default of periodicity. What does that mean? If we had just this here, yeah, we have a map which goes from index n to index n minus 2. Yeah, and so if this was an isomorphism, then this would express that infinitesimal K theory is periodic. But in general, it's not the case. And the default is given by the Hochschild groups. Yeah, Hochschild groups as the failure of periodicity of infinitesimal K theory. Yeah, of periodicity too. Yeah, like unitary K theory. Yeah, topological, unitary topological K theory. And so, along these lines, Lode tried to do the same link, yeah, to group homology or Lie algebra homology as before. We had that the global K theory are the primitives in the group homology of GL infinity. We had that the infinitesimal K theory are the primitives in the Chevalier-Eilenberg homology of GL infinity. And now we ask ourselves, are the Hochschild groups primitives in some Hopf algebra? Yeah. And so this is Lode Cuvier theorem, and Cuvier was a student of, or is still a student of Lode, and they showed that the when you take the tensor algebra on the Hochschild groups with degree shift, like for infinitesimal K-theory, then you get a Hopf algebra, and it is in fact the Leibniz homology of GL infinity of A. So the failure of periodicity are the primitives in some Hopf algebra given by the Leibniz homology. Leibniz homology. And so here comes the first major step by Lode. He was able to lift up the Chevalier-Eilenberg differential from the exterior algebra to the tensor algebra. Here comes the step lifting the Chevalier-Eilenberg co-boundary operator from exterior powers to tensor powers. And therefore he defined Leibniz homology. And so by what we said before, this Leibniz homology in some sense measures the failure of periodicity in algebraic K-theory, but only on the infinitesimal level. And so now Lode asked, is there an algebraic structure such that Leibniz algebras are its infinitesimal objects? And this algebraic structure, which he didn't know and which we maybe still don't know, he named Kopsigul. Which is kind of a very strange French word for denominating a mythical bird, which had been seen by some people, but whose existence could not be established. So it's kind of a very elusive thing. And so, but actually, you can read this in two ways. And you can read it either in the way that only the infinitesimal objects of this algebraic structure must be Leibniz algebras, or you can read it in the way Lode told it. You can ask for into which integrate Leibniz algebras. You can read it in both ways. And actually there are then two questions. First one is integrate. Find the structure into which Leibniz algebras integrate. But there's a second question. In fact, Lode did not so much care about this structure. Why? Because he just wanted this structure in order to have its homology theory. Because only and you don't want to have this structure, but you don't only have to want its homology theory in order to apply it to GL infinity of A, yeah, and this would measure the failure of periodicity in algebraic K theory. Yeah, you want to apply this homology theory only to GL infinity of A, not even to an object which is genuinely of this structure. Yeah, yeah. So this is why kind of this first problem was not really his problem. Yeah, he did not really care about the objects. He only cared about the homology theory. And so the second question, which is much more a Lode question, was verify that its homology theory satisfies the Lode conditions and we will come to this later. Yeah, Lode had in his paper, which is called on conjectural K Leibniz K theory, on conjectural Leibniz K theory. In his paper, he has a list of properties this homology theory should satisfy in order to work well with the existing results on K theory. So actually, my student Simon Covès gave answers to questions 1 and 2. Yeah, in his thesis, he integrated Leibniz algebra, integrate Leibniz algebra into Lie-Racks. But in his thesis, he only integrates into local Lie-Racks. Yeah. And so, in some sense, the algebraic structure of racks or Lie-Racks fits into this framework, but only up to like 80 or 90%. Yeah, there is still a 10 or 20% missing. Yeah, meaning that it does fit, but it does not fit so well. Yeah, it does not satisfy all the demands Lode had on such a theory. So you can interpret this in two ways. You can say, okay, maybe Lode's demands are too strong. Maybe we will never find a theory which will do this, and rack homology is good enough. Or you can interpret it as we did not find yet the right structure, and we still have to search. Yeah, but okay. Let me.
What is the meaning of local?
I'll come to this. Okay. Yeah, local Lie-Rack is like local Lie group. Yeah, you have a group structure only in some neighborhood of the unit element. Yeah, and this neighborhood should be closed under the rack product, and yeah, so it's kind of a long definition, so I won't give it, but you can imagine that it lives only in a neighborhood of it. Okay, now let me come to the first question. Integrate Leibniz algebras into Lie-Racks. So the meaning of integrate here is the same meaning as integrate a Lie algebra into a Lie group. Yeah, there are several ways to do so, and I won't review them, but there are so-called Lie's theorems, Lie's first theorem, Lie's second theorem, Lie's third theorem. Lie's first theorem says that you can, for every, when you are inside a Lie group, and you take a sub-algebra of Lie algebra, then there is a sub-Lie group of this Lie group, such that its tangent space F1 is the Lie algebra you started with. The second theorem is about integrating homomorphisms, and the third theorem is about integrating abstractly a Lie algebra into a Lie group. And you can do this in several ways. For example, there's Ado's theorem, which tells you that under some conditions a Lie group, a Lie algebra always has a faithful representation, and so up to, then this faithful representation lives in some small GL of a big vector space V, and so you can pass to big GL, the group GL of V, and then you're inside a Lie group, and then you can do the integration mechanism from the first Lie theorem, in order to have a Lie group integrating your Lie algebra. This is one way to do it. Another way to do it is using the central extension given by any Lie algebra, and we will come to this in a moment, because this is how Simon Covès integrated Leibniz algebras into local Lie regs. But let me first talk to you about the meaning of this problem. Actually, for any Leibniz algebra, you can also define a reg product simply on the vector space H. You can, for all x and y and h, you can define x regs y. This means e to the n x of y. What does that mean? The add, small n, means the homomorphism from GLH to GLH, which sends y to x with a bracket. It's like in Lie theory, it's just the bracketing operation. And so add x is a derivation of the bracket. This is the meaning of being a Leibniz algebra. Add x is a derivation. And so e to the add x is an automorphism, because the exponential of a derivation is always an automorphism. And so this already shows you that this bracketing operation acts bijectively. And we have the reg identity, self-distributivity identity, because when we compute this, then we have on the right hand side we have e to the n x of y, which acts on e to the n x of z. Now this is the right hand side. And now there's a formula for e to the n alpha x is in fact for alpha in automorphism, This is alpha e to the n x alpha minus 1. Yeah, this is a formula which is rather easy to show. So we can develop this term here, and it gives e to the x, e to the y, e to the x minus 1 or minus e to the x, e to the x, and z. Yeah, and now you see that this cancels, and we get the left side. Yeah, so this is an easy way to construct a rank product on the vector space H of a Leibniz algebra itself. Yeah, and so this is not what we want. Yeah, because in Lie group theory, we want Lie groups which have an interesting topology, yeah, which are not just vector spaces. Yeah? So somehow this is not what we want. Yeah, and so therefore, in order to make this a meaningful problem, yeah, one has to say something further. Yeah, we don't.
The differentiation of this rank is the original Leibniz algebra.
Yeah, it is. It is the Leibniz algebra we started with.
Oh, okay. And
this is Leibniz algebra we started. This is not the problem. Yeah, exactly. Okay. Yeah, I should have said this. Thank you.
And the zero vector is 1, right? So it is a pointed rank also.
Yeah, it is a pointed rank. Yeah, exactly.
Okay.
So, but this is not what we want. So in order to make this a meaningful problem, we have to specify something more, such that, so the one thing one would like to have is that in the special case of Lie algebras, we get the answer we already know. Yeah, such that in the special case of Lie algebras, we obtain one connected Lie group corresponding to it. Okay, this is now it is a meaningful problem, and so the first answer, the first kind of trivial answer, is not possible anymore, because now this Lie rank is always on a vector space. Yeah, and so what Simon Coves did was to any Leibniz algebra, we have a short exact sequence which goes like this. In the Leibniz algebra, you have the ideal of squares, and when you divide it out, you get the canonical Lie algebra associated to it. And so this is the ideal of squares. Generated by all the x for x and actually, yes, there is a method to integrate Lie algebras into Lie groups by taking the canonical central extension, which is associated to any Lie algebra. Yeah, when you have a Lie algebra, you have its center and the so-called G add, yeah, which is G divided out the center, yeah, and so this G add lives inside a GLN, yeah. This lives inside GL of G, yeah, and so it is a Lie algebra of a Lie group, yeah. This integrates into big GL of G, and The center is just a vector space, so a trivial Lie algebra integrates into a vector space as a Lie group. And so when you want to integrate a Lie algebra into a Lie group, according to this method, you only have to integrate a cocycle, because this central extension is uniquely determined by a cocycle, a Lie algebra cocycle with values in this center. And so there's the method of 1S, which shows you how to integrate the Lie algebra cocycle by integrating around path in the Lie group in order to make it a Lie group cocycle, and then you from there you can integrate the Lie algebra into a Lie group by putting together the pieces here with the cocycle. And so this is what is known from Lie group theory, and Simon Covès did more or less the same, but for this sequence here. So what is we have here a Leibniz algebra, but this is a Lie algebra. So this Lie algebra integrates into a Lie group, and this ideal of squares is in fact a module over this Lie algebra, but a Leibniz module over this Lie algebra, and there's a cocycle involved. And so what Simon Covès did in his thesis was to integrate the Leibniz cocycle, which comes up here, into a Lie-Rack cocycle. And so this satisfies this requirement, but gives, unfortunately, only a local Lie-Rack. And so maybe I can say one more sentence on this. The ingenious thing he did in his thesis was it is very difficult to integrate the two cocycle. The two cocycle, difficult to integrate. But what is easy is a one cocycle, because one cocycles of a Leibniz algebra and of a Lie algebra are the same. Because Lie algebra cohomology is on the exterior product, Leibniz cohomology is on the tensor product. But for degree 1, there's no difference between the exterior and the tensor product. So one cocycle you can integrate, but two cocycle, difficult. And so the main idea of his thesis is to express the two cocycle as a one cocycle with coefficients in one cocycle. And so he could integrate it. But okay, so this is one way of doing it. But
sorry, before you go on, may I ask you a question?
Yes, sure.
So I was just wondering if that doesn't take you too far afield, what goes into the integration of this Covès thesis? Is it similar to Van Est sort of integrating along triangles method? I'm wondering specifically, like, go ahead.
I don't remember in detail, but you're starting at 1 and taking paths, going to group elements. And then
So my question is in Van Est method, what you do is that you create a form that is somehow invariant with respect to the group structure. So how does the rack structure allow you to move your form around?
Yes, it does not. But you're not on a rack. You're on a Lie group. You're on the Lie group.
Oh, all right.
This is always the thing I'm trying to say, try to go back to the classical objects. Yeah, here you integrate this Lie algebra into a Lie group, and then you only work on this Lie group. Yeah, or on the Lie group, on the product Lie group with this vector space. Yeah.
I see. Thank you.
So this is why Van Est's method works for the one cocycles, and so the crucial idea is to translate two cocycles into one cocycles with values in one cocycle.
That makes sense. Thank you.
Or I should say, one cocycle with values in one cochain. Okay, yeah, this was like 12 years ago. He did his thesis in 2010. So unfortunately, I don't remember the details very much. I should have prepared this in order to say more about it. Yeah.
We switch to cover. You speak of cosine.
Yes, this is cohomology here. The central extension, or this is not a central extension, this is an abelian extension, is always given by a cocycle, a two cocycle. Yes. Yeah, I'm okay. With respect to the motivation, I switched. That's correct. Yeah, the motivation is more on the homology side, and this is kind of a very general feature. Yeah, and the fathers of this subject, Lode, Jean-Louis Lode, and Teimuras Pirashvili, they almost exclusively worked with homology and right actions. Yeah? And so in the business of doing differential geometry with it, yeah, you can imagine that acting from the right is not a good thing to do. Yeah. Vector fields act on functions from the left. Yeah? Try to write everything in differential geometry on the right, and you will see that you will be lost very quickly. So from the beginning on of his thesis, we translated all Lode Pirashvili stuff into left stuff. Yeah, in order to do differential geometry. But this is only a suffering. Okay, now there are different attempts of integrating Leibniz algebras into some global geometric structures, and I cannot do the catalog of all of them. But let me talk about what we did together with Martin Bordemann. We have a theorem which integrates augmented Leibniz algebras into augmented Lie ranks. Yeah, this is exactly according to the philosophy I told you yesterday. Translate everything into the classical structures, integrate, and then translate back again. And so this works, but there's a caveat, which is that it is not functorial, unfortunately. Yeah. And why is it not functorial? Because it involves in a conjugation invariant neighborhood of the unit element in a Lie group. Yeah, and this cannot, at least to our knowledge, this cannot be defined naturally, functorial. Yeah. So our theorem in 2017 is so when you have an augmented Leibniz algebra, yeah, meaning this is a Lie algebra, which acts on the vector space H, and P is an equivariant map with respect to the action here and the adjoint action there. Then Z is the kernel of G, G prime is the image of G, and you can integrate to G being the Lie group integrating Gothic G, and G prime being the Lie group integrating Gothic G prime, and integrate the action. And then you get a theorem like this. There is a smooth map S from G prime to G prime, such that S of 1 is 0, and S T1 of S is C identity, and S intertwines the actions of G on G prime and G prime. In fact, yeah, what I did not tell you is from the axioms of an augmented Leibniz algebra, it follows that this G prime is in fact an ideal in G. And so it makes sense to, so it is closed under the action of G. And the affine bundle, which is a pullback of the affine bundle P from G, now considered on G prime, pulls back to a Dirac N. Yeah, which is just a pullback, so it is such that P of X is equal to S of prime. Yeah, this is a bundle over E prime. And this affine bundle is a Dirac, having the property which I'm just erasing, meaning that when you start with the Lie algebra, you get back a Lie group. You get back the Lie group given by this Lie algebra. Yeah, and so let me just call it this property and not write this again. And T1 of M is as Leibniz algebra. Yeah, and so in fact, this is not very interesting. The only point which is kind of interesting is the first point. Yeah, why can you have such a smooth map? And this was known before us. This is not our achievement, and it actually it goes. It's very nice. Yeah, I recommend that you read on at least this part. This is done in our appendices, and it comes from determining a neighborhood of 0 in the Lie algebra on which the exponential map is diffeomorphism. Yeah, and this is a very nice subject, and it leads to very classical things like the characteristic polynomial, yeah, plays a role, and maybe I won't talk about this too long. Yeah. For example, what comes into this first point, one interesting thing is, I don't know whether you know this. Yeah, when you have a map sending Z to a polynomial. Yeah, this is a polynomials in lambda with highest coefficient 1 in of order n. Yeah, and in fact, this induces the homeomorphism. T from T to the n over S n to this. Yeah, so this is one ingredient. This is symmetrical. Yeah. This is one ingredient, and then we use the characteristic polynomial, and we have open neighborhoods. Okay, now let me not dwell too deep into this, but this is very nice. I recommend read this in our appendix. Okay, so this was about this first question of Lode, but in fact, some years later, Simon Covès answered the second question. Yeah? Second question was this homology theory, and we are talking here about RAG homology or RAG homology, should satisfy some properties. Yeah, and Covès showed several of these properties in the framework of cohomology, not homology, but this is kind of interchangeable, yeah, in Lode's requirements. So what is RAG homology? So R of RAG and M in R module. Then there's a code chain complex CRN of R with values in A. Which is just the maps in the sense of set theory from R to the N with values in A. And on these cochain spaces, we have co-boundary operators. And so the co-boundary operator is the sum one and yeah, so it is a little bit like in all these other cohomology theories. It's an alternating sum, but now not of one operator, but of a difference of two operators. Yeah, and one is as an index 0, and the other one an index 1. Yeah, but both of them have the I index. And so the DI 0 n plus 1 of F on n+1 elements is, if I'm not mistaken, this is the one where we take out the ith element and act on all the following elements. Correct. This is the 0 one, yeah, exactly. And so here is the last one here, which does not do anything, is the xi-1 here. Yeah. And so we go up to xi-1, do nothing, and then starting from the xi, we act on all the elements which are beyond. And the one term is the one with the action. This is xi, right, x1 up to I breaking on f yeah, and so here, as this is a non-associative operation, one has to say what one means by this object. Yeah, and so I mean the composition of these maps. Yeah, where Cx on Y is X ranks in Y. Yeah, I mean the composition of these maps, and so it is. So it is stated in the associative language. Okay, this is RAC cohomology. And maybe in order to, actually what one would like to do now is compute this RAC cohomology for some examples. Yeah, but this is unfortunately what I will not do, because this is more the kind of thing you do in non-theory. Yeah, in non-theory, you want to RAC co-cycles in order to enhance your linking variance or not invariance. And so this is kind of a little bit far from our subject, and so this is what I will not do, but I encourage you to do so. And so in order to do a computation, let us consider the case where R is A or G in a abelian group. Because this is one thing Lode demanded for this homology theory. It should give a certain result on abelian groups, yeah, and on this, so the homology theory should give on abelian groups H, L, or G. With trivial values should give G to the N. Yeah, this was one demand. Yeah, so let us see how this fails for RAC homology. Yeah, so this is one reason why RAC homology is not considered to be the correct homology. Yeah. So indeed, the di0 n+1 of f in this special case, yeah, this is the conjugation action here. Yeah, but the conjugation for an abelian group is trivial. So here we just have x1, xi minus 1, and then xi plus 1, xn plus 1. You agree? And then the other one once again, this is the trivial conjugation operation, so it doesn't do anything, and we are with trivial values. I didn't tell you, but A in this special case here has trivial values, so this also gives stress x1, I minus 1, x5, x1, yeah, and so you see that in this difference here, the two terms cancel, and so the co-boundaries operator is 0 in for the abelian group, and so the homology is just G. It's just the space of cochains, yeah, and so now the critical point is that it is all set maps, yeah, it is all maps from G tends G to the N to K. This is much larger than would have expected Lode. Lode would have expected that this is the, yeah, or let's say that we can see. Lode would have expected this. And so, in some sense, it's not correct thing. Okay, this is for the bad news. But the good news is that Simon Corrèze showed that many of the properties which were expected to hold for this exotic homology theory do hold for the RAC homology and cohomology. So the theorem is when you have a RAC, B group, A and associative algebra, seen as a trivial G module and seen as a trivial R module, yeah, then HR, this RAC homology, yeah, I'm sorry, I didn't put the R. The RAC homology of R with A is graded densely formed algebra, and maybe I will not tell, yeah, what does it mean to be a densely formed algebra? Dendry form means that there are two kind of products, yes, which satisfy strength identities. Maybe I should not write all of them. Let me write all of them. Yeah. So when you look at them, then you see that in fact some of them look like an associativity, but you switch around an object, switch around, yeah, kind of between the left and the right structure, there is kind of an associativity. But then, okay, then you have more complicated properties. The upshot is that when you do this minus, yeah, right minus left, gives you an associative product. Yeah. So this is one of the properties, and the second property he showed was there exists a morphism of graded algebras from group cohomology to the rank cohomology of the conjugation rank associated to the group. And this is injective for dot one. In fact, Lode asked more. Yeah, Lode asked not only injectivity for degree 1, but actually Lode asked that it is an isomorphism for degree 1 and injective in degree 2. Yeah, and this is kind of inspired by Leibniz cohomology, and the Leibniz cohomology people in the audience will agree with me that in Leibniz cohomology you have of a Lie algebra isomorphism in degree 1 for exactly the reason I told you 20 minutes ago. One being a one co-cycle in the Leibniz cohomology or in the Lie cohomology is the same, at least for trivial coefficients. And then you have an exact sequence, yeah, in Leibniz cohomology. And so I think Lode was inspired by this to say that in degree 1 you should have an isomorphism, and in degree 2 you should have an injection. Yeah, but this does not seem to be true in this. Conj of A is a conjugation reg associated to the group G. Yeah, thank you. So
excuse me. So could you roughly give the formula of this standard form algebra?
Yes, no. I wanted to tell you now that this is a very complicated theorem, a very combinatorial theorem, and even understanding just the formula for the left and the right is needs some preparation. Yeah, you have to talk about shuffles and.
Okay.
It is very combinatorial. So I can. So what I prepared to tell you about this theorem is to give you an impression, yeah, where it comes from. Yeah.
Yeah. But, why there is such a structure? Yeah.
Okay. But unfortunately, I cannot be very precise on this. Yeah. So please read his paper. It's very well written and very nice paper.
Okay, thank you.
Yeah. So how to show this kind of theorem? Yeah. So analogy. Let me try to explain the combinatorics which are involved in this theory. Yeah. So what happens is when you have a group, yeah, then you have a category. The category with one object and the elements of the group being the morphisms on this one object. Yeah, and then you can do something which is called the nerve of category, which is you have to take the nerve is a simplicial set where the n simplices, simplicial set S or n like nerve, where the n simplices are the set of n composable morphisms. And composability in this category does not mean anything, so any morphisms. Yeah. G1. Yeah, now maybe is it n or n plus 1? Let's say just n. Yeah, and so now on this simplicial set, you have the simplicial operations. Yeah, you can go to n minus 1 by omitting an error in this composition. Yeah, you omit it, you go from I minus 1 directly to I plus 1. Yeah. This is one of the simplicial operations, one of the phase maps. Yeah. And then you have degeneracy maps, which go in the other direction, which insert an identity, or here the group identity, yeah, the group unit at one place. Yeah. Okay, this gives you a simplicial set, and then you have the geometric realization of the simplicial set, and this gives you a topological space, which has as its singular homology the group homology of G. And so for Rex, the story is very similar but different. Yeah, and what is different is when you start with a rack, the right structure to put here is not a category. It is what is called a trunk. Yeah. So why are categories intimately related to groups? Because a category can be defined as being a graph, yeah, with distinguished triangles. Yeah. And what is a trunk? A trunk is something in this sense, but it is a graph with distinguished squares. Yeah, and the squares we are looking at are the following. Yeah. So what replaces the composition or the product in the group category world is here given by distinguished squares with the rag product here. Yeah, and so a trunk is a directed graph with distinguished squares and having and then there's a more sophisticated version of a trunk, which is a corner trunk. Yeah, meaning that when you are in a cube and three of the squares are distinguished, yeah, then you can complete to a distinguished cube. This is the corner axiom of a corner trunk. So to every rack, you can associate such a corner trunk, and then you have a certain cubical nerve, yeah, which is a cubical simplicial set, yeah, which is gotten combinatorially out of the trunk associated to the rack. And this cubical nerve has the same cohomology as the cohomology of the rack. Yeah, and you can imagine in this cubical simplicial business, yeah, the how to say it, you have in fact, yeah, let me talk about the cubical category 1 second. Yeah, its objects are the graphs. The N, where the vertices are the subsets of and do such a subset of 1 N, yeah, you can associate an element in 0, 1 to the N just by saying whether IK epsilon k is 1, if A is an A and 0 other one. Yeah, so this is a combinatorial description of the simplicial nature of a cube. Yeah, in a cube you can always be on the in every coordinate you're just either 0 or 1. Yeah, these are the faces of the cube. Yeah, and so morphisms generated by the Chase maps. Yeah, and so this gives you the cubical category, which plays the same role as the category delta, the simplicial category delta in simplicial sets. Yeah, and so the cubical simplicial set, what is called by Simon a pre-cubical simplicial set, is a functor from square opposite to sets. Yeah, and I think he calls it pre-cubical only because it is kind of a pre-sheaf. Yeah, it does not satisfy any sheaf condition, so it is kind of a pre-sheaf. I think the pre comes from there. But okay, what I wanted to say is rack cohomology is intimately related to this cubical simplicial combinatorial stuff. Yeah, and so in this sense, the article constructs combinatorially these left and right products on the cubical nerve of which is associated to a rack. Yeah? This is what is done in this paper. And so yeah, yeah, sorry. About the nerve? What? Sorry?
Cubical nerve.
Yes.
How we do.
the cubical node is a function from delta from square up to 6. And so we have to define it on any subset. Yeah, for this I have to define to you the corner trunk associated to a rack. We have seen that the distinguished squares were these. So there's still just one object. And yeah, let's say more or less for n equal to 2, I think, yes, for n equal to 2, the objects here are the squares in, yeah, and so these squares are sent to the distinguished squares in the corner trunk, yeah, and yeah, and then it is generated by these squares. Yeah, let me say that. Yeah. It's too vague, but one should enter in this combinatorial business. Yeah. And actually, this is kind of, and nowadays I see on the archive more and more papers about cubical simplicial stuff. Yeah, somewhat late because like 70 years ago, Jean-Pierre Serre defended his thesis on where he used cubical simplicial stuff to show deep theorems in homotopy theory. So somehow people or mathematicians had needed lots of time to digest first the simplicial theory, and now comes the cubical simplicial theory. Yeah, so people working on cubical simplicial theory are kind of exotic, yeah, but it is very worth studying. Yeah. Okay. Okay. Yeah. Unfortunately, I cannot say much about this. Simon would have been the better speaker about this, certainly. Maybe I can talk about more recent developments in rack homology and cohomology. Rack homology related to a bias network. This is a collaboration by many people we know and like. Koves, Farinat, Lebed, Victoria Lebed, who is now a professor in Caen, and Manchon, Dominique Manchon from Clermont-Ferrand in 2019. And what they do is they show, actually they study the non-commutativity of the cup product in the rack cohomology. Yeah. Yeah, and so what they show is the rank homology complex. Not the homology, but the complex with the cut product is differential graded associative algebra. Which is commutative to explicit homotopy. So this is what they construct: the explicit homotopy, which determines the failure of the commutativity of the rank homology complex. And in fact, it is Denry form, as we already seen, and Zinbiel up to explicit. Yeah. So how do you have to read this theorem? If you don't like exotic structures, just read the first part. Yeah. And in order to explain where these the first part comes from, it comes from the exotic structure. Yeah. Courbet already showed that the rank homology complex is dendriform. And so what these four authors show is that it is in fact Zinbiel, and this is the way of speaking about commutativity of dendriform algebras, yeah, up to an explicit homotopy. Zinbiel is an algebraic structure, which is in fact the Kosul dual of Leibniz. Yeah? And so exactly as the cohomology of a Lie algebra is commutative, yeah? The operatic cohomology of a P algebra for a P Kosul operator is an algebra over the Kosul dual operator. Yeah? And so here the Kosul dual to Leibniz is Zinbiel. Yeah? And this is still a word play by Lode. Yeah? It is just Leibniz read backwards. Yeah. Okay. And okay, this is the result. And how do they show it? They show it by using differential graded bialgebra, yeah, which computes rank homology, cohomology. It is the abelian group generated by some generators x and e to the y for x and y are, and divided by some very natural relations, x y times x minus xy, and e x or xy x minus x e y. Yeah, and so for all x and y in R. Yeah, so you have to understand that this is clearly true for when the rank product is just group conjugation. Yeah, then it is x, y, x minus 1 times x, this gives x, y. Yeah, and here it's not so easy to say where this comes from, but these. So for the moment, I gave you the abelian group. This is graded, so I have to give you the degrees. Degrees 0 for the x's and 1 for the these exponentials. Yeah, you can call them exponentials if you want to. And it is differential graded. Yeah. So what is the differential? The differential of x is 0, and the differential of the exponential is 1 minus x. It is a bialgebra, so it has a co-product, and the co-product is that all the x's which come from the rag, they are group-like or set-like, and the exponentials are primitives. And so what they show is, that this bialgebra is very much related to the cohomology of to the rag cohomology. Yeah, in fact, the cohomology of this bialgebra gives the rag cohomology with values in the associated group of the rag. So this is kind of a new development, and I think there are lots of things to understand in this direction. So maybe I should stop here.
Okay, thank you very much.
Yeah, what?
So are there any questions or comments?
Yeah, maybe I should give some comment. I was very proud of my thesis student, Simon Coves. Unfortunately, he didn't find a permanent position in academia, and this was very sad for me.
Where is he now?
He is in, I think he is a math teacher in Istanbul, in a French school in Istanbul.
High school?
High school, yeah. French high school in Istanbul. He chose this.
Yeah, so he did a very excellent job. Yeah. Yeah. So so I think the formula, the explicit formula of the coboundary operator for a rag
Yes.
also motivated from that cubic stuff.
Exactly. And yeah, and what I did not say is this co-boundary operator, why does it satisfy dr squared equal to 0? This comes from the cubical identities, which are the analog of the simplicial identities in the simplicial stuff.
Yeah, so it is very complicated. Yeah, I can imagine. Yeah.
It needs some acquaintance, to get with these formula, but then it can be equally easy or difficult than the simplicial stuff.
Okay, so another question is about that dimension algebra. So that cohomology, there is a dimension algebra structure. So so we require it is a trivial module. So it is a trivial module. So yeah, what happens if it is not a trivial module?
Very good question. Very good question. I don't have an answer to this question, and this is certainly a good thing to look at. So the question could be which algebraic structure we need on this coefficient module in order to have a dendriform structure on the cohomology algebra with coefficients in this module. Yeah, very good.
Yeah. So another question is also about this cohomology. So does the second cohomology of a rag can classify, for example, central extensions of rag?
Yes, I think this is in yes. This, I think it is not Simon who did this, but people like this N. Jackson. I wrote you an email about. Yeah. I think
Okay.
either he or even people before, because this extension question is very important in this Nichols algebra business. Yeah, it is some subject in Hopf algebras to classify what they call Nichols algebras. Yeah, and there are racks coming in, and so rack co-cycles there give extensions of racks and help to classify Nichols algebra. I cannot be more precise about this, but yeah, this is true.
Yeah. So I'm sorry. Another question. So about this Reich cohomology. So are there some relation between this Reich cohomology and the corresponding cohomology of the Leibniz algebras?
I will talk about this tomorrow. Yes, when you have this is what this is contained in Simon's thesis. By the way, Simon's thesis is also very readable. It's written in English. It is publicly available. Yeah. So
okay.
Please open his thesis. Very nice thesis, and it's written in there that that there is a morphism from the cohomology of a Lie rack with values in. Yeah, he does it only in with values in symmetric, no, anti-symmetric or symmetric modules. Yeah.
Yeah.
Go to the corresponding Leibniz cohomology, and maybe I can sketch the proof of this tomorrow. Yeah, it's
okay. Thanks.
It's just differential geometry. Yeah.
Yeah.
Differential of a function in n variables.
Yeah. Okay, so now there's a question in chat.
Okay. Does there exist some compatibility between the cup product and dendriform structure on cohomology? Oh, very good question. If I remember right, maybe I'm mistaken here, but if I remember right, these dendriform structure, when you do the left minus the right, yeah, then you get the associative structure, and then you get the cup product, if I'm not mistaken. I think this is the relation.
Okay, thank you. So, are there any questions or comments? Okay, so if no questions, so let's thank the speaker again. Thank you. So
we meet tomorrow for Leibniz cohomology then.
Okay. So see you guys tomorrow at the same time. Okay, see you. Bye-bye.
Bye.